me just get started recording. So okay, well, as I promised last time, I like to talk about kernel PCA, and of course I probably will give a kind of a review of PCA, maybe a little bit elaborate. So, but PCA is kind of important, some kind of very important knowledge, principle, how to spell that, principal component analysis. So it's basically any analysis. So any kind of knowledgeable data scientists, engineers, computer scientists, should know that basically. So and kernel PCA is an extension of PCA, like what we talked about last time. Kernel SVM is projecting your features from low dimensional space to high dimensional space. Okay, I forgot to pull out your chat so I can see it if you guys type any messages. Oh wait, I didn't even share screen. I'm so sorry about that. Yeah. So okay, here you can see that. So and okay, this is just motivate a little bit. This thing I'm grabbing from something known as a Eigenface, actually a paper from Eigenface. So what it is basically just you have phases, and then you project using PCA to have different major component, or that basically the principal components of the phases. This is showing the principal components here. I will elaborate what does that mean afterward. But you then each of the phase you can think of these are the linear combination of this eigenphase, or basically just a fancy name of eigenvectors. Actually more precisely would be eigenvectors of the covariance matrix of this data here. And any of the phases can be kind of linear combination of this. So then you can use this as features to do classification. So for example, eigenphase, yes, eigenphase can be used for phase recognition. So I can have a phase coming in, I'll project it into these different eigenphases components. So then the projected coefficient will be the features basically. So for example, I have this input phase here. I will just literally do a dot product of this phase with each of these components here. And then I will get coefficient, I don't know, A1, A2, and so on and so forth. Then this in this case here, I will have 15 features, right? So these 15 features I will use for as a input for the classifier instead of taking the original image directly. So, but I will elaborate more what PCA precisely generate these components here. And then here also motivate a little bit the kernel PCA. I'm here is an example trying to do denoising using both PCA and kernel PCA. You can see kernel PCA is way better. This is kernel PCA. This is PCA. So I have this is the original image coming in. Now I project it to the bases, basically different bases. I essentially you think of the bases that only for example in this case only first 15 components are important, and the rest are not important. So for the rest, I will simply ignore them. So then I reconstruct the original image using just these 15 components. Then I will get a denoising effect because I basically just take the important components and ignore the other components that most likely to noise. So this gives me some kind of denoising like this one here, but I can do much better denoising if I project first to high dimensional space. So any question for the moment? So
I guess is it just that it's easier to separate the features in the high dimensional space, kind of like that?
Yes, because one example. Let's see if I have an example here. Oops. So I didn't open that. I need to first open that. Oops. Move to here now. Okay, let's go back to put this aside here. Okay. So here, like this is an example that like I have like several classes here, several clusters here, right? This is our parent clusters. I want to separate them. And if you know PCA already, so I will explain later on, but if you know PCA already, what PCA does is I look at the major axis, right? Here, like I cannot find any major axis because it's kind of symmetric, right? And also like there's no way that I'm able to separate these clusters in just the original space. But on the other hand, if I do a kernel PCA, I can first project to a higher dimensions. Then these clusters will in high dimensions, like this, I'm showing the first two kernel PCA component. So then it's kind of separate, like this does not perfectly separate this like green and white classes here.
But you're only looking at two of the dimensions.
Yeah, it's only two of the dimensions.
This makes it very clear. Thank you.
Yeah. So okay, let's see. And so let's get into some math now. So okay, so let's start with PCA. So idea of PCA, like, as I mentioned here, is like, for example, I have a 3D data here. So let's see why I didn't get to my, okay. This is some data here, like they say 3D data. So what we are looking at is like we want to find the axes there that have like most variation. So, and also like for simplicity here, I'll already assume the data is zero mean. So for example, like if my data is not zero mean, for example, the origin is here, so I can always subtract the mean of the data to shift the origin into the center, right? So it doesn't, so for simplicity, therefore, like we always first subtract the signal with its own mean, so we get all the data zero mean. So then like in this case, you can see like this will probably like this will be my most important component here. So the one in blue here is the direction have like the strongest components, but because it's has highest variation along this direction, right? And then the next one probably is the red one. We want to look for this red one, right? And then like then this light blue one won't be very important. So basically, so then the idea is that we want to look for this axis, like have the highest variation, the direction have the highest variation. So okay, I will give like really all the math here. So actually, honestly, the math for PCA is very elegant though. Like so I guess it's like some of this engineering math that is it's not like very tedious. So if you understand it conceptually, it's very nice. And it's the beautiful part of engineering math. Like some of this engineering math is extremely tedious and ugly. So, but to start with, like I need to show. Okay, I start with like I need to talk a little bit background, like with eigenvector and eigenvalue. I assume that you guys already knows that, but it's a little bit of revision in case you guys get rusty. Because the last time I guess I also mentioned like under what situation like the eigenvectors, actually more precisely the eigenvalues, will be real, right? So and I asked that because that's an important type of matrices, square matrices, basically the Hermitian matrix, or actually in the more specific case would be the symmetric matrix that will always give real eigenvalues, and also more importantly, the eigenvectors of these matrices will span the entire space. And this eigenvector span the entire space, and also the eigenvectors will be orthogonal to one another. So in other words, I can find like a v1 is equal to lambda 1 v1, and so on and so forth, like all these eigenvector here. Let's say a here, say n by n, so up to a vn equal to lambda n vn. And I can find vn, v1 up to vn, they are orthogonal to one another. So vi perpendicular to vj if I is not equal to j. And also I can make them normalize as well, like vi is equal to 0. So okay, here is very tempting to show this because it's a very neat proof for that. So first of all, like I probably didn't, I'm not sure. Like, how many of you know what is Hermitian? Or like on top of your head know what is Hermitian? You probably like heard of that before, but maybe you don't kind of remember that on top of your head, maybe. Basically, I have like Hermitian of a matrix is just equal to the transpose and then do a complex conjugate. So this is a generalization of a transpose basically. So if you have like matrices are complex, then you will be interested in Hermitian rather than like just transpose. So now what's going on is like if you have a matrix is Hermitian, that means that like the Hermitian of the matrix is equal to itself. Then let's first show that like the eigenvalues will be real. So I will have like, then this will imply that like I have any eigenvalue a v, let's say equal to lambda v, then lambda will be real. So this is one of this, again, a very neat proof that I can help to do it, like because it's also like only need 2 minutes to show. So let's consider a v v Hermitian like this. Note that I have like a b Hermitian will be equal to a b transpose and complex conjugate, and will be like equal to b transpose a transpose complex conjugate will simply equal to b transpose complex conjugate and a transpose complex conjugate. So therefore, a b Hermitian is just equal to b Hermitian a Hermitian. So I will need to use this here. So then if I consider this guy here, this will be equal to, I can consider on the multiplied by v on the left hand side. So I have v Hermitian a v, but a v is just equal to v Hermitian lambda v, right? So then lambda can pull out. So I have lambda v Hermitian v here. But on the other hand, I can also like multiply this on the other side because a v Hermitian is equal to a Hermitian v Hermitian, right? Just basically from here. So then like a Hermitian, but I already assume that a Hermitian is equal to itself. So that a Hermitian is just equal to a. So I will have like a v Hermitian v. So a v is equal to lambda v, then Hermitian v here. Then this will be equal to, know that like when I apply Hermitian to this value lambda here, because Hermitian is equal to transpose and complex conjugate, right? So I will have complex conjugate of lambda, or maybe I use star here as I used earlier. Lambda star v Hermitian v. So therefore I have lambda v star v Hermitian v is equal to lambda star v Hermitian v. So therefore I will have like lambda is equal to lambda star. Yeah. So any questions? So therefore, like I basically will get this to be real. Now I can also show that. Let's see. This actually I just repeat here. Let me just also show that. Let me erase this now here. If a matrix is Hermitian, then if I have like two eigenvectors, let's say V1 is equal to lambda 1 V1, and A V2 is equal to lambda 2 V2. So if lambda 1 is not equal to lambda 2, then I will have V1 and V2 are perpendicular to each other. So the inner product will be just equal to 0. And by the way, this inner product will be V1 Hermitian V2. So assuming these are column vectors, it's equal to 0. And again, I can prove that like with the basically in the same manner, consider like A, I have like maybe V1 Hermitian V2 here. Now do the same thing, I can multiply this side. I have like V1 Hermitian AV1 is like lambda 2, sorry, AV2 is equal to lambda 2 V2, right? So I can pull lambda 2 out. Here I have V1 Hermitian V2. Or I can consider multiplying on this side. This will be like A Hermitian V1 Hermitian V2, but like A Hermitian is equal to itself, right, again. So therefore it's equal to A V1 Hermitian V2. So it's equal to lambda V1 Hermitian V2. So it's equal to lambda V1 Hermitian. Actually, lambda 1 star. But I know that like from my earlier theorem that like lambda 1 will be real. So therefore like lambda 1 star is just equal to lambda 1, V1 Hermitian V2. So therefore I have this equal to this. So then lambda 1 minus lambda 2, V1 Hermitian V2 is equal to 0. So when lambda 1 and lambda 2 are not the same, then I have to have this is equal to 0, or like the inner product between them will be 0. So with this already like, it's not a complete proof. It already suggested that like you can use the eigenvectors. Like if I have a Hermitian matrix A here, if I have A equal to A Hermitian equal to A, then I can like use this eigenvectors like V1 up to Vn. And in general, I can have like Vi and Vj is equal to 0 when I is not equal to j. And I can also normalize that because all these arguments we just show that like this eigenvector will be perpendicular to one another, right? Of course, here I had actually a tiny caveat here. It's like I'm assuming that like all these V1 up to Vn have like different eigenvalues, but I will just leave it open here. Actually, when the eigenvalue is not the same, you can still do it. So, but I'm not going to show it here. Actually, the idea is like you will have like some duplicate eigenvectors, but you can do some linear combination of them. All of them will have the same eigenvalue, and all of them will be orthogonal to this guys here. But then like, you can adjust this guy to make them like orthogonal to one another themselves. So therefore, like you basically can, whenever you have like a matrix of Hermitian, again, let me repeat again. Whenever like we have a matrix of Hermitian, you can find a set of eigenvectors that span the space n, Rn, actually Cn in general. So let's say like if A is n by n, A is n by n here. So then I can find basis V1 up to Vn that span Cn. So spanning meaning that like if I have any vector in Cn, let's say if I x that's in Cn here, then this vector can be linear decomposed into like sum of like Vi here, Ai equal to 1 to n. And of course, like here, like we'll just focus on like real symmetric matrix. So we don't need to for the discussion of PCM kernel PCA, we'll use we'll assume that A is real. That basically the coefficient of A is real. Then Hermitian matrix is the same as a symmetric matrix, or like basically real symmetric matrix is kind of Hermitian matrix. So I would just say A transpose equal to A, and A is basically real, right? So, but I need to start with Hermitian because this kind of proof like I need to use Hermitian to show that. So anyway, but from now I will just focus on this. So I will have like matrix is real symmetric, and then like they and when there is real symmetric, then I can decompose any vector of length and vector with its eigenvectors basically. Let's see. Yeah, this is just repeating like what I talking here. So now then let's say I have this actually now I use U here. It's okay. Like these are the eigenvectors of this A again. So I have the matrix is a let's say is real symmetric, and I have like eigenvectors like U1 up to UN. They are basically orthogonal to one another. Then I have like A U I is equal to lambda I U I, right? So I can rearrange in this case in this way. I think you probably see this kind of stuff before. So I have like AU1, for example, consider this first one, AU1, it will be equal to lambda 1 times U1, but I can write it in this way, right? So, but when I write it in this way, I can call this matrix O here, this another matrix. It's basically the same matrix O here. And AO is equal to O times this D here is a diagonal matrix. And I can also normalize U here. If I assume if I not normalized, but I assume it's all normalized. So therefore, like I have like UI is equal to 1 here. Then I will have like O, let's say if I multiply O inverse on this side, right? O inverse on both sides. So I have O inverse AO will be just equal to D, right? And then I know that like O is actually known as this orthogonal matrix. Basically is characterized by this property here that O transpose O is just equal to 1. Sorry, identity. Because if you think of like O transpose, now I will have like this row vector here, U1 up to UN. So transpose this guy. Okay, these are all column vectors. Make sure like you guys are on the same page. These are all column vectors. Transpose of this O here will become like row vectors, right? U1 transpose up to UN transpose here. And O is just this guy here. And then when you multiply them, I will just say have this element is just U1 transpose U1, right? The second one is just U1 transpose U2. And the third one is U1 transpose U3. And all this like will be just the inner product of UI, UJ that, I mean, all the off diagonal terms are UI, UJ when I is not equal to J, so therefore it will be equal to 0. So everywhere here is 0. And this is normalized, so therefore it's like all 1 in the diagonal. So therefore like I have O transpose O is equal to identity, or the O inverse is just basically equal to O transpose. And again, I want to emphasize that U1 up to UN will form a complete basis. I have a feeling that like, I'm going quite fast, so I'm let's see. And let me maybe open a new page here. So what PCA does now we have the background for that needed to know PCA from linear algebra. So we say that like if we have a complex, sorry, not complex, if we have a symmetric matrix A, then if like if I have symmetric matrix A, then let's say this is like n by n real matrix like A that is symmetric, And then for any vector in Rn, it can be represented by linear combination of the eigenvectors, let's say. So I have like V1, Vi, I equal to 1 to n, Ai, so something like that. So, or like I have like Rn is spanned by V1 up to Vn. So and now we get back to the picture. We want to consider that for PCA, we have some data points in oh, actually, before that, I guess I should give a revision of covariance matrix. So just in case I also like not sure how many of you have this kind of background before. So let's say I have a vector like x here. It's a random vector. So I have x is composed of like x1 up to, let's say, xn. Now, the covariance matrix of x is just equal to, basically the matrix is just equal to the covariance of each of the coefficients. So for example, like the diagonal element here would be like just x1 minus x mean of x1. So expectation x1. So basically diagonal is just the variance of that element x1 here. And then I have this second element here will be like x1 minus expectation x1, x2 minus expectation x2. And basically this pace here will be the same here. And okay, again, let's assume zero mean. Assume this whole vector, whole random vector is a zero mean. So I will have like this all is equal to zero to simplify a little bit. So if these are all zero means here, so I will have like covariance of x here is equal to expectation x1 square, expectation x1, x2, expectation x1, x3, and so forth. And then this is expectation x2, x1, x2 square, like that. So now one thing again, like you can consider, okay, I can write like this, but note that the diagonal is basically just the variance, right? Sigma 1 square, sigma 2 square, and so on, right? I can kind of like write it, I guess you may consider as a tautology, that the off diagonal term I will write like this instead. I can have like write expectation x1, x2 as sigma 1, sigma 2, rho 1, 2, and sigma 1, sigma 3, rho 1, 3, and so on. By the way, anyone know what's the name for this rho 1, 2? Rho 1, 3? There's a name for this kind of like coefficient here. Or basically, if you see that like rho 1, 2, therefore is like equal to, or let me maybe in general, like rho ij is equal to, okay, the meeting seems to go on. Let's see what's going on. Yeah, it's shut already, so I'm not sure like what's going on. So anyway, so rho ij is therefore is actually equal to expectation xi xj over like expectation xi square, expectation xj square. And of course, I am assuming zero mean. So if it's not zero mean in general, it should be something like that. Xi minus xi bar. So xi bar is the mean of xi. Xj minus xj bar. And expectation xi minus xi bar square expectation xj minus xj bar square. So anyone know the name of x of Oj? There's a technical name for this kind of stuff. Yeah, okay. Did anyone see this kind of stuff before? Like,
correlation coefficient.
Yes. This is the correlation coefficient. And actually, the correlation coefficient is like it's always bounded by like 1 and -1. So, and also like this is kind of tempting to show this. Why it's like between 1 and -1. Again, it's like 5 minutes doing that, but it's like very elegant again. So actually this is a special case of like so-called I mean, when I say like what Ij defined this way is within 1 and -1, this is like basically saying that like xi xj square is less than equal expectation expectation xi square expectation xj square, right? And this is a special case of this Cauchy-Schwartz. How to spell that? Okay, I'm not sure how to spell that. I think it's something like that. Inequality. So anyone came across this before, like this inequality before? So I will make this poll question as a question. Just want to get feedback. Like anyone like see Cauchy-Schwartz inequality came across that before, like in somewhere? So actually, you may came across that like in high school, like no, anyone get feedback? Like this is a poll question, it's a quiz. I consider, I don't know, like extra credit. Just a yes no question. Just want to see like okay, yeah, that's good. So you by the way, like you may came across this before. Actually, I came across something like this in high school. Pure math is like xi xj. Let's see. Yeah, okay. I equal to 1 to n, some j equal to 1 to n is less than equal to, xi square, I equal to 1 to n, xj square, j equal to 1 to n. Or actually I can, yeah, actually, wait. Oh, actually I can have x and y to be different, right? So I maybe like xi. Oh, actually, I should write like this instead. Yeah. Xi, yi, the square of this guy, this is I, I'm sorry, like this is I, is less than equal to xi square and yi square. So this is the form I kind of came across that in high school, but actually that's a, you see, like that's lots of like similar form for that. This is basically just a general result in linear algebra, or like in the Porter space more precisely. So you can say like for any vector like x and y here, I have xy square is less than equal to x XX times YY. So this is like just the inner product of X and Y. And I can even have like X and Y in compact space. So if X and Y in compact space, this inner product will be correspond to compact inner product. So it means that like XY here is actually equal to X, the Hermitian times Y. If I have real like X and Y are real, then like XY will be just equal to X transpose Y, something like that. So okay, 2 minutes to show that, just like the sketch for this. Because the property of inner product, so if you can define something as inner product, that supposedly that you have like X, the inner product is linear. So for example, if AX plus B, Y inner product with C is equal to A, X, where A and B are scalar here, X and Z plus B, Y and Z, and also like they have some symmetric property. For example, like X, Y is equal to Y, X. Actually, in general, I need to put a bar here, or like put, so let's ignore that. I assume that things are real. So XY is equal to YX, and so on. Like for the inner product, I also like this XX to be bigger than equal to 0. So because the inner product itself like is like specifying with itself is specifying the norm. So the norm better to be bigger than equal to 0. Now then with this thing here, this is basically just the definition of inner product. So I can consider like, for example, X plus TY, X plus TY. This inner product has to be bigger than equal to 0, right? Because of this guy here. But because of the linear property, I can expand that. I have like XX plus basically if like TY multiplied by X and X multiplied TY, I have 2 of them, 2T XY. Okay, by the way, like T here is scalar, T here is scalar, X and Y are vectors. And plus like T square YY, right? So for this guy to be bigger than 0, then if you remember, like in high school, you have this kind of quadratic equation, right? So the quadratic equation, the solution of a quadratic equation in general, let's say AX squared plus B X plus C equal to 0 should be something like X is equal to minus B plus minus B squared minus 4AC, something like that, right? Over 2A. I guess I kind of like, I'm not sure, like I got the exact formula here. But the problem is that like, if I have that, this thing here bigger than equal to 0, so it means that like I cannot have any solution for T, right? So I cannot have any solution for this guy here. Maybe I put this here as T squared. MT B plus BT here. And my A here, in this case, A is a YY, and B here is a 2XY, and C here is a XX. So when this guy I know is like bigger than equal to 0, then I cannot have this case here, right? I cannot have this case. I cannot have 2 solutions here. I can at most like 1 solution, maybe even no solution. So for my case, I should have something like this, or like maybe another case, maybe something like that, just hitting this point here. So therefore I will get 1 solution. So therefore I must have this part here is less than 0, right? Because if I have like this part is bigger than 0, then I will have like 2 solutions. So therefore I will have B squared minus 4AC is less than equal to 0. So B squared is again is a 4. So B is a 2XY. B is here, 2XY. So it's a 4XY squared minus 4XX. That's A. C is YY. Should be less than equal to 0. So that basically give me this thing here, give me the Cauchy-Schwartz inequality. And note that like here is very general, right? As long as I can define some kind of like inner product for some vector space, then it will work. The Cauchy inequality will work. So in this case here, I can define my inner product as a with some random vector x and y. The inner product is basically just equal to expectation x and y. And then you can show that this kind of property holds. So therefore, like I will immediately from Cauchy-Schwartz inequality, we'll have this is basically equal to xx here. And this is a yeah, this is the y here. So therefore, I will have this guy here. So therefore, like I will have the sorry, correlation coefficient will be like between -1 and 1. So okay, anyway, like yeah, can't help to talk about that because it's actually pretty nice. So and okay, let's give some physical meaning of this correlation coefficient. Okay, maybe you guys would be more interested to do some physical meaning here. So I have maybe I make a couple more pages here. That's hard to take. Okay. So let's say I just give you something like as a question like to choose. I say so I have like these 3 cases are the data. This is just 2D, like 2D data. Like so, this is the data point basically. So I have like x is like a random variable that I sample in the space here. So I have like x1 is this axis, x2 is this axis, so on like x1, x2, x1, x2. Now all of them are basically zero mean data. Now, which one is rho 1, 2 is equal to maybe 1? Case A, case B, or case C? Yes, that's good. Yeah, that's very good. And okay, this is the first question. And then let's ask one more question. Which one is rho 1, 2 is equal to 0? Okay, that's very good. That's very good. So in general, like for example, like okay, how about this one? What do you expect the rho 1, 2 will be? Like it should be yes. And yes. Yeah, okay, yes, that's very good. So it will be like between 0 and 1. So it will be, yeah, it will be, so you see that like when x1 is larger, like x2 tends to be larger as well. So you have a positive correlation, but there will be some correlation, but it is not to the extreme is equal to 1. So when you have case like this, you will have 1. For example, like if I have other line here, what's rho 1, 2 here? Again. Okay, very good. So I trying to trick you, so you are not getting into the trap. So note that the slope here is not important. Like you can get like really infinitely flat, but as long as like you have a straight line here, like this angle is bigger than 0, then will be 1 to be equal to 1, because then you have one of this variable is basically just a exact scale value of this another variables. So they are actually are completely correlated. So okay, that's good. Now I can really talk about PCA now. So I think I have all the background now. So for PCA, so I have some data point, right? So for example, like some data point here. So it's already zero mean. So therefore the origin is in the middle here. So I want to find this axis, right? So like the largest axis first. What's the largest axis here? So I can find it by saying that like I want to find the projection, because let's say if I call this as u, this direction as u, right? I should have like the expectation of u transpose w. This will be basically, for example, like let's say if y I call w, I'm sorry, like times x here. What I mean is that if let's say if I have point here, right? So I want to have maximum variance along this direction, right? So if my u here is a normalized, so let's say I also like constrain u to be 1, the norm is equal to 1. So then it's just a unit vector. So then like this is x here, let's say x particular instant of x. Then u transpose x will be just the projection, right? It will be just like, sorry, I'm not sure whether you can see it clearly. It will be just the projection like this one here, right? And this is like the projection onto this one here. So I want to find this direction u such that this projection is as big as possible in terms of magnitude. So then I probably want to put a square here, right? So I want to make this as big as possible, such that like also u is have a unit norm. So I want to maximize this. So this should give me the first principal component. It's my u here, should be just like this, right? So you agree with this formulation here? So if I have like any data, like let me draw some other data set here. Oh, okay, just I got a silly question again. Like, so which one is u? So this B or A? Which one is u that I'm looking for? Okay, some of you get that, but some of you are not actually not. So this is the principal component. This is the one I'm interested in. I want to find the direction that the data is maximally spread. So this is the direction I'm interested in. And to find this direction, I want to project each of the point here, or like to this axis, right? To this axis u here. It can be any axis. For example, I can project this guy here, project this all this point here along this one, but the projection will be somewhere here, right? Will be this place here. And if I compute the variance will be just this, basically computing the projection, the variance of the projection, right? Then the variance will be just like that big, right? But on the other hand, like if I project into this direction, the variance will be this big. So this is like more preferable, right? So so therefore, like I'm basically just maximize the projection to some direction u here. I don't know what is u here. I try to maximize that. But I need to make sure u is normalized. So that's how I'm going to do that to find the principal component. Is that clear now? Okay, so yes. Then okay, let's continue this formulation. So I have like u transpose x square can be written as by the way, u transpose x is just a scalar, right? So it's a projection now. So it's a projection of some value here. And I can write it as a u transpose x transpose u, right? So because a u transpose x is a scalar, it's just equal to x transpose u, right? So I have square of that u transpose x, u transpose x. This I can write it as a x transpose u instead. So it's equal to u transpose x, x transpose u. So then I have this one here, maximize over u, and have the same condition here. And now I have only x are random variables, right? U are not random variables, so they are scalar value. So I can have my expectation get into that equal to this, because u does not depend on x. U is just as constant with respect to x, and do that way. Now what I'm doing now is I use the discussion we have at the beginning. It's that we see that like expectation x transpose is this covariance matrix, and also the covariance matrix is symmetric, right? Because okay, let's see if I have that somewhere. Like I have this expectation x2 x1 is equal to expectation x1 x2, right? So it's a symmetric matrix basically. So therefore, like from our discussion, where is it? Yeah. So from our discussion at the beginning, if I have a symmetric matrix, then the eigenvectors of the symmetric matrix can span the entire space, right? So therefore, I can write any u as linear combination of the eigenvectors of C here will be equal to Wi, let's say Wi, Vi. So Vi are the eigenvectors. These are the eigenvector of C. Right? I equal to 1 to n, I say. And note that like because u is normalized, Wi, by the way, W1 square plus W2 square, so on, should be equal to what? For u to have like the norm equal to 1, so I have like u should be equal to 1, right? So u here is like Wi Vi I equal to 1 to n. Wi Vi I equal to 1 to n. Then this will be equal to, or maybe I put one of them as j instead of I. J equal to 1, have different dummy variables here. Then I have like I equal to 1 to n, j equal to 1 to n. Basically, I can use the property that inner product is linear, so I can get like Wi, Wj, and then Vi, Vj, right? And Vi, Vj, know that these are orthogonal eigenvectors because I see symmetric, these are orthogonal. So this will give me just a delta ij function, right? So it's just a delta function. And so therefore this becomes just one sum here equal to wi equal to 1 to n, wi, or wi square, right? And note that this is equal to 1, right? So therefore the sum of wi square is just equal to 1. Now, okay, like I say, like for any u, I can represent with this guy, right? And and you also have a constraint of the norm equal to 1, so therefore it's equal to, I mean, sum of wi's is equal to 1. Now then I substitute this u into here. Let's see, into here. So then I have, let me erase here. Oops. I have like u transpose cu here that I'm trying to maximize, right? I'm trying to maximize this term here is equal to sum over I equal to 1 to n wi vi c j equal to 1 to n wj vj. And okay, this I should have a transpose here. And then C is Vj, each of them are eigenvectors of C, right? So therefore this become sum over J equal to 1 to n Wj lambda J Vj, right? So basically C multiplied to Vj here, get lambda J Vj, and have like Wi Vi transpose I equal to 1 to n. So then I have like I equal to 1 to n Wi. Well, I can pull the summation to the front. So it's j equal to 1 to n Wi Wj lambda j and Vi transpose Vj. But this again is just in the product, right? Vi Vj, and it's equal to the delta function, right? So therefore, like this again becomes just one sum here, I equal to 1 to n Wi lambda I. And so I just basically have like Wi square lambda I. Okay. And remember, I have this constraint here. Now let's assume that like my eigenvalues are sorted descendingly. So I have lambda 1 is bigger than equal to lambda 2, lambda 3, lambda 4, and so on. So what should I pick W such that to maximize this one here? Remember that now my formulation become maximized U transpose CU. This thing is actually equal to sum over lambda I square, sorry, lambda I Wi square, I equal 1 to n, such that sum over Wi square is equal to 1. So if I given you this, I should optimize over U that is actually basically optimized Wi, right? So what should I choose for W? It's a kind of a question here. So if I know this, what should my W's be? Yes, but can you go even more extreme? Anyone want to give an answer, like as a quiz question, like besides like Jifeng like gave a try. So again, like we start from like that formulation, trying to maximize this projection, right? You transpose x square for u, the norm is equal to 1, right? Such that maximize u. And we say that, like, okay, after like decomposing u into eigenvectors of like c, then we get a conclusion is basically that u transpose, basically this term here is just equal to sum of like lambda I and wi square, and with a constraint like the norm of u is equal to 1 is basically equal to this guy here. The sum of wi square is equal to 1. So what's the maximum for w here? How do I maximize this guy here? So the question is, how do I maximize here given this constraint here? Yes, we can just choose the first one is 1, right? So we said like W1 is 1. Oh, sorry, y is 0. And all the rest is just equal to 0, right? That will give me the maximum value of this guy, right? So that, and when we do that, like what do we have? We basically just have like u is just equal to v1, right? So therefore, like will be just equal to the first eigenvectors here. So therefore, like this is actually, this proof that like this is actually nothing but just the eigenvector of the covariance matrix. And actually, with the same argument, you can easily show that then the next eigenvector will be pointing with the next largest eigenvector. Or next eigenvector with the largest eigenvector. The eigenvector with the next largest eigenvalue will be the one that have besides the second principal component basically, and you can go like continue to solve. So therefore, like PCA, maybe a summary, like the whole procedure will be, if you have like data x here, you first say subtract the mean, so you have like x is equal to x bar, subtract the mean, then you compute the covariance matrix C here, compute C, and then afterward you can just sort the eigenvalue, and then like according to your sorting, then the sorted the eigenvectors, the corresponding eigenvectors of the sorted eigenvalues will be just the principal component. I'm not going to write it here. So in practice, I'm not going to that one, but instead of like typically you have a data set here, right? If I data set X here, and instead of like first computing an estimate of the covariance matrix, you can just take the data set and do single value decomposition, then the eigenvector, the single vectors with the largest eigenvalue will be the principal component as well. So it's very easy to show actually. But I'm not going to that. Now let me get to kernel PCA. Hopefully I have enough time to just probably not. So the idea of kernel PCA is I will have my covariance matrix I see here at the beginning is approximate. Let's say I have like data point here. I want to, oh sorry, why I write that? I want to approximate the covariance matrix, right? So covariance matrix is like this, right? So and I want to approximate that with some data points. So let's say I have like data point like x1, maybe I write like this x1, x2, this is the data point. Maybe I have like k of them, xk, maybe k of them. Then I can approximate this as like this as 1 over k. Should I use n in my notes? Okay, hopefully I won't mess up myself. K, fine, sorry. X I X I transpose. This is just approximating like this covariance matrix, right? With K data vector here as your training data basically. Now note that like what we are computing like for this C here, like in SVM, we just care about the inner product, right? This is like actually this is not precisely inner product, but in the same token, like we want to have a projection to higher dimensional space. So we don't want to look into just the actually this is actually the outer product. The outer product of like 6i and mxi transpose here, but I want to look at the mapping to higher dimension. So this is like basically map to very high dimension of this instead. And I will consider this K. This is of course this covariance matrix will be in the high dimensional space. This is not the same C. Maybe I don't know how. Maybe I just put the H here to kind of like specify this is a high dimensional space. So I want to consider this instead. But we get into the same challenge that like we don't know this mapping in general. We don't know this mapping in general. We only know the inner product. Let's say if I have phi x, phi y. So we have some kernel function to estimate this. So this is like part we know. But note that this is different. Like this is a outer product. Like the inner product is equal to phi x transpose phi y instead. You see the transpose is exactly on the opposite side. So and what we now what we want is like if I have like phi xi here are the basically xi again, like xi are the data point, right? The data point that I have. 5xi is like mapped to the high dimensions, right? So let's say if I have the eigenvectors, again can be decomposed by this phi here. So I assume that like my V eigenvector can be written as a 1 to k alpha I phi xi here. So basically in the high dimensional space, I have this phi xi here is the data vector in the high dimensional space. Am I trying to find the eigenvector that is linear combination of that? And actually, I can show that of course, I to think of like how do I know this is actually the eigenvectors? I want to make sure this is the eigenvector of CH, right? So it's I hope that like this will be like CHV is equal to lambda V for some V like representing this form here. Luckily, it turns out it's really the eigenvector is really equal to this guy, and it can be shown pretty easily. So just know that I have CHV is equal to lambda V here. Maybe I just copy from here, that will be quicker. So here CH, I call it C here. So let's say if this is an eigenvector, I have CV is equal to lambda V, right? And C is just, okay, I'm sorry, like this, I use N here now. Here, like I have N data point here instead of K, so maybe I can put a K here. And this is my C anyway, it's my C earliest or CH earlier. So this one here, know that like this is a column vector, this is a row vector, right? So V is also like a column vector. So therefore, this is actually a scalar, right? So this is a scalar. I can move it up here, like this is a scalar, multiplied by this guy here, right? And this thing is equal to lambda V, right? So I can have 2 lambda down here. So therefore, like I will precisely have like V is equal to this thing here, right? And this whole thing is like just a scalar, right? So it can be considered that exactly the alpha I here. So therefore, V is actually a linear combination of this phi here with alpha I here, with alpha I some weights here, alpha I. So then the question here is like, what is alpha I though? Like we need to look for alpha I. Okay, I guess I have 2 minutes. I'm kind of watching that. I guess I will just pause here, then like continue next time. I want to make sure if you guys have any question, also like maybe even any other question regarding homework and so on. And you also, I guess you are supposed to submit. Wait, this is a kind of low. I hope that, yeah. I hope you can hear me clearly. So I guess this is not the mic volume though. So and also like we have this near for other assignment for your presentation abstract also, and also the project proposal. So and for presentation abstract, I think it's like I forgot what, like maybe it's still like couple weeks left. But
Yes, on the website here on Canvas, the project proposal is due on the 27th, and the presentation abstract is due on March 6th.
Okay, so yeah, okay, so it's like, so, and I want to just say like ahead of time that like you guys have a kind of a expected schedule. So after the submitting your presentation abstract, expect that like you are going to present like approximately after 2 weeks. So then like will be let's see, the 6th, then like you submit that maybe in 23rd, like you start like to present that. Like I'm kind of expecting like maybe 2 presentation per day, not to kind of pack it too much. So we don't have like many of us. So it can be done like in about 2 weeks, I guess. So and again, like for the presentation, you can talk about like packages, or you can talk about interesting papers. I always came across lots of interesting paper. I don't have time to dig in all of them. So and if you find anything interesting paper, you can talk about that. Or if you like to just talk about like recent packages, for example, like you have torch lighting. I don't know, and lighting, like I'm not sure how many of you like came across that. Like it's basically like similar to like fast AI, like or like similar to Keras on top of TensorFlow. So it's trying to make some of this boilerplate code just like removed. And it looks quite convenient and very nice. And recently I toying with some idea and like play with something called like weight and biases. It's actually really nice. So I mean, like for free for academic, I guess. And this is very nice if you have lots of models that you want to try. Then you have like lots of hyperparameters that will automatically upload when you run your code. You automatically upload your result to the website. So therefore, you can get a very quick report, like seeing like, okay, maybe I would just, let's see if I have it here. For example, like here, I have like, for example, this one here, I have many ones here. You see, like I won many times, and each time have like different, a little bit different configuration, right? So I can see like quickly like the loss here, like for each of them, and I can also like I prepare some plot here. Okay, this is like some of this, and I can get a filter to what I'm going to show, and or like maybe just look at like, for example, I'm interested in one of this case here. I can easily go back to see like what is the parameter I use. For example, like for this one, I'm using like Galut here, and like have my sigma is like this. I have like 3 sublettered and so on and so forth. So it's like some pretty nice tools. So there are many of like this like out there. So like I may try to get one of my students to talk about torch because he's more familiar than me, so probably will give a better talk. But you guys can also explore it and with your presentation basically. So do you have any other questions? If not, I guess I will just stop here. And I guess I will have a request for like for extension for the homework. So I guess we will just extend to Tuesday, and then like just post any question if you have problem like on this. I mean, just post any question on Discord if you have any problem. Yeah.
I just had a quick question about the
Yes.
this whole concept of subtracting the mean value.
Yes.
So there's a couple computer vision
Yes.
deep learning applications where the authors they've subtracted, for example, there's this like div2k data set.
Yeah.
And the authors have subtracted the mean value, the mean RGB value of the whole data set before training their network with it.
Mm-hmm.
And I'm wondering, I guess, is the reason for that the same or similar to the reason that, for example, in the PCA, we're subtracting the mean value, or is that is there a different reason for that?
Yeah, actually, this is very standard practice. It used to be not even subtract the mean. It's often you want to even normalize the data when people use the old school like processing. Like for example, like okay, this I cannot go back. Okay, I can go back. So oops, I don't know why that. I probably need to stop that. Let's see. I think it's just the university saying that tomorrow will be like normal. So it's often that like you will even like kind of like normalize your data to to kind of like decorrelate your data. Those, for example, we start with data like this here. I may kind of like find a rotation such that I will shift the data like to be normalized, and then like I can even scale the data such that like they have same variance like, in all axes there. So this kind of like pre-processing is important like for old school, like for example, like I'm not sure SVM, like, but for like from for many classifier, this is actually necessary. And but now with deep learning, like often like these kind of pre-processing can be ignored, but subtracting the mean is still like good practice actually. Like if you don't subtract that, most likely you will just the net will subtract it for you. It will start with like adding a bias
Oh,
in the
yeah,
first
it just
layer,
finds a
like, yeah.
bias.
But I mean like yeah, this is not actually major. It's not really major. Yeah.
Okay, yeah, see, thank you for letting me know
Yeah.
though. I appreciate
Yeah.
that. Okay, thank you.
Yeah, sure. So okay. So I guess if no more questions, I will see you guys next week then.
Bye.